And yeah, first of all, thank you to the organizers. It's a both initiative with this talk series and targeting like UG/PG students. And I really hope both benefits of your interaction or it's better that more and more students join Korea, and then they all can get benefit and then interact with the and in future PhD core abroad, then they will have some ideas, like if they have some questions, how to apply and everything about that. So okay. Slide, can you see my slides?
Yes, your slides are visible.
Okay, great. Okay. So more obviously I'll start with my introduction, but already you want to need an introduction decide. So I will just add a few things like my subscriber homework Najjar, and mo BSc more course to Jorhat Institute of Science and Technology, GISTUP, and then masters are more PhD Tishpur University Pro. And PhD karane moi collaborate course lo Ayuka Pune to eta Astrophysical Board Bhal Institute India. And I'm like really thankful to have that opportunity, like Ayuka Professor Ranjit Mishra lagot kaam korislo tate more PhD kampur shika hoisil, and more PhD karane more mainly I started with like data analysis astronomy, and the data analysis board experts as Ayuka channel ko board help best located time out. So yeah, there was a very good opportunity as Mukarne. And PhD karne moi pleasures like active galaxy kam course, which I'll be talking about. Our PhD karne, I was closely working with Astrosat data. Astrosat is an Indian satellite, into launch was 2015 not, into multi-wavelength satellite. So and Astrosat karne data utilize korbo karne during my PhD, my ISRO project to come course for 1 or 2 years, and tarpasat moi like South Africa join korlo as a postdoc. Tatu more come like active galaxies then supernova remnants come hoisel mainly. Aru apart from X-rays for my first postdoc, my has collaboration join course to work on very high energy gamma ray data. And tarpasot in 2023, like this year July, my EPC join Kurlu, and yar murmin kam hose like my continue Korea so active galaxy come and very high energy observations. But apart from that, I also started working on like neutrino astronomy. I'll talking about neutrino astronomy later, and I joined like Game Trinity collaboration. So this I'll be talking about. So we'll see. So to begin with, okay, let's start with something that we all are familiar with. Moi talk to English team to and I'm fine with both English and Ohomia. To question in any, you can ask me in any language, it's fine. So okay, so let's start with electromagnetic radiation. And yeah, okay. So electromagnetic radiation, we all know, like these are the radiation we experience in our everyday life, like every day, and it helps us in different ways, like starting from like we see the light, photons, these are electromagnetic waves, then heat, communication, then transfer, medical purpose, and whole load of purpose, right? So this electromagnetic radiations are like radio wave, microwave, UV, IR, X-rays, gamma rays, and all this radiation we call collectively as electromagnetic spectrum or radiations. And yeah, so here we can see the electromagnetic spectrum. Here, if you can see my cursor, so we see all the wavelengths here, like radio, microwave, infrared, ultraviolet, X-ray, and gamma ray. And here from, if we go towards the like right-hand side, we see that this is the axis of increasing energy, and you know how the energy is related to the wavelength. Here we measure like 2 parameters. One is wavelength and the energy of the photons. Like we know that like photon has dual nature, a wave and a particle. So we can measure these quantities. And starting with radio, which has the longest wavelength but the lowest energy. And if we move towards the high, gamma ray, it is the increasing energy and decreasing wavelength. So basically, the gamma ray or X-ray have much higher energy and lower wavelength compared to radio. So this is the electromagnetic spectrum. So out of all this electromagnetic spectrum, we can see only the tiny window, like the visible light VGR, we can see, and other wavelength we cannot see. So to detect that, we need special detectors, and we'll be talking about some of the very high energy gamma ray emission in this talk. And talking about energies, this is the energy of the photons we are talking about, and the energy that we measure in terms of electron volts. And this energy, we know that is associated to wavelength, and in UV and IR, this energy is associated with a particular temperature. So if we know the wavelength, it can give us information of the temperature of those of a system. And now the important one, very important fact about this electromagnetic different radiation is that if we talk about astrophysical sources, the sources seems very different at different energies. For examples, on right-hand side, I showed an example of one astrophysical source, which is like a nebula, a region of gas and dust. And here we see that this source seems very different in different energies. And here, to represent a particular wavelength, I'll use the term energy that I'm more comfortable with. So here we see that in visible light, it looks more extended. But when we go to the higher energies, like say gamma rays, we see that the entire emission is concentrated at the center. So the basic idea is the sources look different in different energies. And this is the reason we need different type of telescope to understand this type of source better. And also, to order to get a complete picture of the source, we need multi-wavelength observation. And moving on, so what are the lights that we can observe from Earth, like the visibility from Earth? So not all wavelength or energies we can reach on Earth. We have a tiny window, like only 2 windows, where our Earth atmosphere is opaque, transparent to the emission. Like this is optical and radio. Only for these 2 wavelength, our Earth atmosphere is transparent to the emission. That means we can receive that emission on the Earth surface. But all other wavelengths like microwave, infrared, ultraviolet, X-ray, gamma ray, they're opaque to the Earth atmosphere. Why? Because of the interactions and absorption. So this particles corresponds to like ultraviolet, X-ray, microwave, infrared radiations. They get absorbed in the Earth atmosphere, or due to some other interactions, we do not see these lights. So this is the reason we spend so much money building this space-based telescopes and send it to the outer space to observe all these radiations. So what are the ground-based observatories we have is like radio observatories, then optical, and very high energy, which I'll be talking about later. So up to gamma ray, we know that this is happening, but something very interesting happened at the very, very high energy gamma ray. Okay, so when we talk about gamma ray, we're talking about the particles with energy like a giga electron volt, that is 10 to the power 6 electron volt. So electron volt is the unit of the energy, this photon energies. And when we talk about very, very high energies, we talk about energies up to 10 to the power 9, like giga electron volt, or 10 to the power 12 electron volt. So at very high energies, something very interesting happens. And because for these energies, we have actually ground-based telescopes. And this is very interesting. How do we detect this very high energy gamma ray from the Earth? So I'll be talking about it later. And okay, so this is the multi-wavelength scenario. So let's see some more sources. So this is on the right-hand side. On the top panel, we see a very like the stunning view of Milky Way from the southern sky. So this picture was taken from Namibia. And here the red dot shows the galactic center of our Milky Way. And on the bottom panel, these are the galactic plan, like this region of the Milky Way at different energies. So here we can see this galactic plan in gamma ray, then in X-ray, optical, infrared, then and then in radio. So we see that it seems different at different energies. Basically, how do you read this map is like these are the color maps. So say, for example, this gamma ray map here, the brighter color is like the brighter sources. So there the emission is more. That's how we read the maps. So yeah, so these are we see that the source seems different in different energies. Then, okay, so here in this talk, I'll be talking mainly about the gamma ray, not optical, not infrared, only gamma ray. So meaning that I'll be talking about the radiation having very high energies up to 10 to the power 6 or 10 to the power 12 or so on. So this we call as like gamma ray. And okay, so here in the slide, we can see this is called a celestial sphere. So if you have studied like basic astronomy course, you know what is a celestial sphere. So it's basically a sphere centered on Earth, where we can have the measurement of different astronomical sources in different coordinate system. And here the radius is infinite because our inverse is infinite. We don't know the size, of course. And this is the gamma ray sky observed by a Fermi telescope, and this is the galactic plane. And this bright color you see here on the plane, these are the TV gamma ray emission from different sources on the galactic plane. So this every tiny dot is a source. So the sources are more concentrated on the galactic plane, and if we go away, the emission is a bit low. And we see a lot of point-like and the diffuse emissions here. So if we take a zoom version of this galactic center, we see these emissions. This is the zoom version of this region of the galactic plane. So this is in gamma ray, say energy from few mega electron volts to giga electron volts. And here we see that this region is concentrated with a lot of sources. And then this is the bottom panel I showed, the same region in a different energy, even at the higher energy. So here, the energy is about like 10 to the power 12 electron volt. And here we can see the center of our galaxy, the galactic center. So we see that although both are gamma rays, this is the low energy gamma ray, this is the very high energy gamma ray, we see different pictures, like different sources. Some sources are more prominent here, but not here. This is because they are emitting at different energies, and also because of their two different instruments and with their different sensitivity. So the main idea is that in gamma ray, we see like even if a gamma ray is a broad energy range, and within that energy range, we see different properties of this kind of sources, astronomical sources. So when we talk about the galactic plane, there are different kind of sources, as I mentioned, and the sources are something, they are called different kind of sources like supernova remnants, pulsars, PWN. Okay, let me tell you what are the sources. So the supernova remnants are basically what happens is the sources when a massive star dies, it exhausts its nuclear fuel and they can no longer support itself against a gravitational collapse. And then it explodes. And this explosion is called supernova explosion. And whatever left out at the core can be a black hole or a neutron star, or the expanding material, we call them as supernova remnant. And pulsars are basically a rotating neutron star, and they emit in pulses. And then PWN, which is like pulsar wind nebulae, these are basically the interaction between the particles emitting from the pulsars with the medium. And then the different stellar cluster, and there are some identified sources, then diffuse emissions. So all these sources are present here on the galactic plan. And then if we go away from the galactic plan, we see different kind of exotic sources. These are called active galaxies, then blazars, then I'll be talking about active galaxies later. Then GRBs like gamma ray bursts. So basically these are the flashes of gamma rays coming from the distant galaxies. Then black hole binaries and sources like that. So these sources are very powerful sources and emits very high energy radiations. And here, among all these extragalactic sources, extragalactic meaning very far away from our Milky Way galaxy, the blazars are one of the very powerful sources that emits. These are the very strong emitters of gamma rays. And here in this map, that gamma ray map, these circles here all are the blazar sources detected by the Formula telescope. So there are lots of them. And then talking about active galaxies, okay, so as I mentioned, these are one of the powerful emitters, TeV emitters in the sky. So basically, active galaxies typically look like this. The source that I have shown in the middle picture here. This is one active galaxy, Centaurus A. So these are basically black hole system. Like there's a black hole at the center. Then it accretes matter, the surrounding matter, and form a disc-like structure. And then we see the two jets the two jets emanating from the center towards away from the center. And these are basically relative outflow of matter, like of particles like electrons and protons. And this system is called a active galactic nucleus, and these are very powerful, like this emits at a very high energies, and the entire system, the balls and the core, we call it as active galaxies. And here I added a video where you can have some idea how it happens. At the center we have a supermassive black hole. It accretes the dust and gas from the surrounding, and we call it an accretion disk. And perpendicular to this plan, we have the jets emanating from the center. And this accretion disk and the jet-like structure, these are powered by the central supermassive black hole. So you see, this is very fascinating how the jets are coming out from the central supermassive black hole. And these jets are very powerful emitters. As I mentioned, these are relativistic outflows of electron, protons, and very energetic particles. And talking about black holes, I'll give you a quick reminder that the evidence of the supermassive black hole. Now we have evidence of the supermassive black hole, which was a very important discovery and led to a Nobel Prize in 2020. So we have the very first image of the black hole of our Milky Way galaxy, which is Sagittarius A. Here's the picture. And that time there were two pictures were released. One is the black hole of Sagittarius A, and another picture is the black hole of M87 galaxy. This is showing on the right-hand side. So this is basically an active galaxy with the jet, and at the end of the jet, we see a supermassive black hole. So this black hole, since it's an active galaxy, the black hole is much, much bigger than our the black hole at the core of the Milky Way. So, and moving on to the jet. So as I mentioned, among the active galaxies, the type of sources like blazars, these are the most powerful. Why? Because what we see from blazars is the emission entirely from the jets. I mentioned, like the jet is a very powerful emitters of all the wavelengths, the energies. So basically this agent classification or active galactic nucleus classification is based on the angle of the jet with respect to the observer. So if the jet is making an angle with the observer, we see all the components like the accretion disk and the jets and the dusty torus and everything, then we call it a radio galaxy. And if the jet is facing towards us, then we see emission only from the jets, then we call them as blazars. So why they're so powerful? Why, if the jet is facing towards us, we call it more powerful? Something very interesting happens here. What happens is, like, we know that these jets are basically relativistic outflows of particles. So the meaning the particles are accelerating at a relativistic speed. So when the particles are accelerating at a relativistic speed, so we see these relativistic effects. And if the jet is facing us, that means the relativistic particles are accelerating towards us at a very high speed. So then the relativistic effects are more prominent. So that's why these sources are very powerful. So if you have studied like in a master's, like basic astronomy or special relativity course, then probably you know what is a relativistic Doppler boosting. So if you study relativistic Doppler boosting, you may have come across with a problem like, okay, so in the, say you're driving a car very fast and you see there's a green car in front of you, but okay, but the green car is actually a red car, not a green car, but you see it as a green car. Then you need, in the problem, you need to estimate the distance at what speed you are driving. So basically what I'm trying to say is that when the objects are moving at a relativistic speed, we see whatever flux we see is more enhanced than whatever it was emitted from the source. So basically, in this problem, when you are basically, say you are driving at a relativistic speed, then you will see a red car appear as a green car, which are more energy. So this is the Doppler boosting, and this is the Doppler boosting. Basically, the idea is that when particles are moving at a relativistic speed, whatever the emission we receive from those astrophysical objects, we see the emission is much more enhanced. And this is we call as the apparent velocity or apparent luminosity. And there are other effects we observe, which is called as a superluminal motion. So superluminal motion is something like where we find that these particles within the jet moving at a speed greater than the speed of light. Why is that? Because of this effect, relativistic effect. And so this is very interesting. This is a very this is an observational effect. So you consider this is a jet of an astronomical source, and you consider a dot, knot, or a blob in the jet. And if you measure the distance it covered in a and the time it took, then you'll see that it accelerated at the speed which is greater than the speed of light. So this is very interesting, and we call it a superluminal motion. And sometimes it is very extreme that we see this kind of a speed about like 50 times of speed of light. So which is very interesting. And when we take the observation of these astronomical sources, and then we observe the flux, we need to correct the flux for this kind of relativistic effects. So we do that in observations. And okay, so now talk about physics, like what are the physical mechanisms that are responsible for this kind of high energy emissions. So one mechanism is, so the main mechanism is called Fermi acceleration mechanism. So basically the idea is that these particles, the charged particles, gain energy in a magnetic field or in a shock front. So this is the Fermi acceleration mechanism. So there are two types, the first order and second order. And the first order, what happens is that particles gain energies by crossing a shock front. So here is an example. You can see there are some particles, say, it's taking time. I think my internet, yeah. Here you can see this is the shock front, and here these are the particles. So particles are speeding up. Basically, they're gaining energy by crossing the shock front multiple times here. So this is called the shock acceleration, and then they escape. And the second order of acceleration mechanism is like particle gain energy in the very strong magnetic field. So these are the physical mechanisms how the particle accelerated up to that very high energy and can emit at an energy up to 10⁶ electron volts. So here I probably, forgot to include a slide about the radiation mechanisms. So what are the radiation mechanisms responsible for this kind of high emission? So basically, the radiation mechanisms are like synchrotron mechanisms. The main mechanisms are synchrotron emission or inverse Compton emission. And in synchrotron emission, it's basically when the charged particle radiates in presence of a magnetic field. The charged particle move in a spiral path in a magnetic field and they emits. We call it synchrotron emission. And basically, when I talk about synchrotron radiation, it emits in the low energies, like from radio up to X-rays. But when we talk about high energy, there's a special mechanism involved. These are like inverse Compton mechanism. So what happens here is like, say, low energy photons, say radio or X-ray, when they interact with a very high energy charged particle, there is the energy transfer happens from the high energy particle to the low energy photons. And this is how the low energy photons gains energy from the high energy particle, and they emit at a very high energy, like in gamma rays. So these are the physical mechanisms responsible for high energy radiations. And then comes the observatory, like how do we detect this observation, high energy observation? So to detect gamma rays, we have a very fine telescope, like Fermi gamma ray telescopes. It detects the photon from 100 MeV up to 1 TeV. TeV is like tera electron volt. It is 10⁻12 electron volt. And so Fermi-LAT telescope is basically launched in 2008, probably, and launched by NASA. And since 2008, Fermi-LAT has made very important discoveries of different kind of sources like active galaxies, supernova remnants, and other sources. And this is a very fine telescope. And other telescope, like, okay, this is in gamma ray up to energies up to 1 TeV. Like, as I mentioned, like gamma ray is opaque to our atmosphere. That means the gamma ray gets absorbed at in our atmosphere due to several reasons, like due to absorption, or there are other mechanisms like electron-positron pair production. So due to these mechanisms, we do not receive gamma ray on Earth. That's why we need a space-based telescope to observe these gamma rays. But when we talk about very, very high energy gamma rays, say up to 10⁶, 10⁹, or 10⁻12 electron volts, there are ground-based observatories. Because, I will explain the mechanism, how can we do that? This is very interesting. And also another reason is that this to observe this very high energy emission, if we want to send a telescope to the space, then we will need a very large collecting area. We need a very big telescope, and there will be a lot of high background cosmic rays and a lot of problems. So that's why we observe them from Earth. And so to observe this particle from Earth, there's a, like I say, there's a very important, very interesting detection technique. We call it okay, so let me explain this mechanism. So what happens is, like, when gamma rays interacts with the atmosphere, they create a lot of charged particle. So we call them air showers. And then what happens, these air showers, these particles, whatever is generated due to interaction of those gamma rays with the atmospheric atmosphere, they emit some radiations. We call them Cherenkov lights. Okay, so basically, this Cherenkov lights are generated between in the interaction between those gamma rays coming from those like astrophysical sources with our atmosphere. And they create a lot of charged particle, and the charged particle radiates. They call it, we call it Cherenkov light, and they form a cone-like structures. And whatever the charged particle generate here, they can travel at a very high speed. That means the speed higher than the speed of light in that medium. And this high speed charged particle radiates Cherenkov light, and we can actually detect this Cherenkov lights. So here we can see, so what happens in this ground-based observatories where we detect this very high energy radiation, we do not detect the gamma rays, very high energy gamma rays directly coming from the source. But what we detect is, we detect this Cherenkov lights that is produced in the from the charged particle that are produced interaction between those gamma rays with the atmosphere. So here I am playing. Here we can see, do you have the audio of this? Can you hear?
We are not getting the audio.
Okay, so let me explain. So what's happening here? This is what is happening here. After interaction of gamma ray with the atmosphere, it creates air shower of particles like this. These are air showers. And then this air showers, the particles emit Cherenkov radiation. And our telescope, the ground-based telescope, detect this Cherenkov radiations. And there is a techniques, what we call reconstructions. By that, we can indirectly, you see this signals, this is the signal of the Cherenkov light at the detector of our telescope. And by detecting that, we can indirectly estimate the direction of the primary photons. So this procedure is called reconstruction. So it's a very long procedure. Very detailed procedure how we do the reconstructions. So basically, this is how the very high energy ground-based observatories works. So in summary, they do not observe the very high energy gamma ray coming from the outer atmosphere. What they detect is like the Cherenkov light produced due to the interaction of the gamma ray with the atmosphere. So here on the left-hand side, we see that this is the air shower produced. And then this telescope, they have CCDs, cameras, and then cameras, they detect the Cherenkov light and something like this. They see the signal on the cameras and they do reconstruction, and they could measure back the gamma ray coming from the astronomical sources. So this technique we call as imaging atmospheric Cherenkov telescope, IACT technique, and this kind of telescopes are called IACT telescopes. And there are different kind of telescope also, like here, as you know, the medium is air. There are different kind of telescope where we use all this kind of medium, the water as a medium. So we detect these particles in a water tank. So they also have a very interesting mechanisms how to do it, but I'll mainly focus on this kind of technique where we detect VHE photons. And the example of these VHE photons are like current generation telescopes. We have like HASS telescopes in Namibia, and then MAGIC telescopes in La Palma, then Veritas in Chile. Then we have one upcoming very big telescope called CTA, Cherenkov Telescope Array, which will cover a very long range of energy starting from 20 GeV to 300 GeV. And this is like a telescope array. They will have many telescopes, small and big size telescope. And the construction has started. So there is just one telescope right now working, taking data, but the construction is going on for this telescope. And this is the next big thing coming up in VHE observation. So then some examples of water Cherenkov detectors are like HAWK. These are like arrays of water tank. Instead of CCD cameras, they have like water tanks and the detectors there. One is like HAWK and one is like Lhasa. Lhasa is in China. There's observatories there, also called observatories in China. And then okay, apart from electromagnetic radiation or very high energy gamma ray, we see other kind of emission. So what other emissions we see are like cosmic rays, neutrino, and here comes to particle physics. So Cosmic rays are basically the charged particle coming from the outer space. So it can be anything like the charged particle, like electron, proton, or heavy nuclei, or any other charged particles. And this cosmic ray was first detected in like long back by Victor Hughes, and it was in his balloon experiment, and it led to a Nobel Prize in 1936 for the detection of cosmic rays. So unlike the photon radiation, cosmic rays are basically the charged particles, radiation of charged particles. And that comes to neutrino. So neutrino is like, they are the particles like electrons, they are leptons. They have mass, which is very low, but they do not interact with our atmosphere, because they do not interact via strong or electromagnetic interactions. This is the reason why we can absorb neutrinos, like those astrophysical neutrinos coming from like a very, very far light years away, and we can directly detect it on Earth. So there are different type of neutrino particles, like astrophysical neutrinos coming from our sun, then solar, these are called solar neutrinos, then the low energy neutrino, and then high energy neutrino. So in the high energy astrophysics, we are more interested in the high energy neutrinos, the particles coming out from the sources like AGN, supernova remnants. So this kind of sources can emit high energy neutrinos. And when you talk about high energy neutrinos, we are talking about the neutrinos, the neutrino particles with energies like 10 to the power 12 or 10 to the power 15 electron volts. So how the sources produce these neutrinos, or this kind of particles? So there are interactions happen in this systems. We call it like proton-proton interaction or proton-gamma interaction. So basically what happened in such systems, say for example, the agent jet. See if what happened if a proton and a gamma ray interacts, then it emits one proton and some other particle called pion. Then this pion particles decay into gamma rays or neutrinos. So these are the interactions where lead to the neutrino production. So these are very high energy processes, and I'll not go detail into it. And after that, to detect these neutrinos on Earth, we have different detectors. Like one is like very big, like Ice-Cube Neutrino Observatory, which is located in Antarctica, and this detector is very big, as you can see, and it is deep buried inside ice. And here the size is very big. You can see it 20 meter buried deep down the ice. And the size, you can see, if we compare the size of this detector compared to the Eiffel Tower, which is a very tall tower, it's a few times of the Eiffel Tower. So what are these detectors basically? What detects these neutrinos? They have this digital module they call as DOM. These are the individual detectors. They detect neutrino particles. And there are other observatories like KMTNet. This is next generation. That means this is still in the construction phase, and this is coming up. So unlike ICE, this detector is in the underwater observatory. So here we need a medium to interact this to nicely detect this neutrino, the particles. And this detector is located on the Mediterranean Sea, somewhere very close to France. And here the detector unit looks something like this. These are called optical modules. And this is the deployment of the dome here. And this is still in the construction phase. And then, so together with all the EM radiation, starting from radio to gamma rays, then neutrinos, cosmic rays, and the gravitational wave, we call it a multi-messenger astronomy. And because if we want to have a complete picture of this extreme emitters, we need to have the information of all the, emissions. So we have to have the complete picture via multi-messenger astronomy. And now I will talk something about my research. What I do is I mainly work on blazars, the sources I have just explained. And what I try to do is like I study various physical mechanisms that is responsible for the jet emission. I basically study the high energy emission coming from these jets and what are the physical mechanism involved or yeah. So basically, when we talk about observation, we basically observe the observation features are something like we call spectrum and a light curve. Spectrum is something like whatever flux we observe versus energy. That means whatever flux we observe at different energies. And the light curve is something like the flux observed at a different time scale. So here the x-axis is the time scale, y-axis is the flux. So the one interesting fact about the sources is that whatever emission we see, the emission varies with time. So these are called the light curve, and we also try to study this variability, why these sources, the fluxes are varying with time, what are the reason behind where we suddenly see a very strong flux at a particular epoch, or yeah, stuff like that. And there is something called, so this blazars or this jet emission emits in different wavelengths, like from radio to very high energy gamma ray. So if we combine all the energies, we see a structure like this, like a double hump structure. It peaks at 2 different energies. So we call it the SED, spectral energy distribution. So in my work, I basically study these SEDs at different wavelength and try to explain the physical mechanism behind this kind of observational features. So we call it as SED modeling. So we have some physical models that can explain all this multi-wavelength SEDs. So these are the science part, and talking about observation, I work with, like I said, high energy observations starting from X-rays. So for my PhD, I have worked with like open source data, like X-ray data. So all these X-ray data are open source meaning that these data are available. I mean, anyone can download this data and analyze and use this data. And I have worked with different X-ray telescope like NuSTAR, Swift-XRD, XMM, and more closely with AstroSat data. And AstroSat, as I mentioned it before, it's an Indian multi-wavelength satellite, was launched in 2015. That time I was in masters. And then I joined PhD and I started working with AstroSat data. And I worked on various blazar sources using these data sets, like few sources are like micron 421 and some very extreme blazar sources. And so these are the X-ray data. And as a part of my postdoc projects, I am a part of very high energy collaboration. So what happens in case of very high energy collaborations, this data are not public. These are like close collaborations. So you can use the data if you're only a part of these collaborations. So I'm a part of HAS collaboration, and recently I joined the Scheme-to-Net neutrino collaborations to use the neutrino data. So yeah, so these are the observations I have been working on. And this is something very brief about my research, what I do. And with this, I end. And at the end, I want to thank you all for your time. And here I take the opportunity to show some of the pictures from my visit to Namibia at the HAS site. So I had an opportunity to visit the HAS site during one of the conferences in Namibia. And the place is amazing for like sky observation. They have an absolute clear atmosphere, and you see a very clear, nice sky. And yeah, so these are the HAS telescope. These are the mirrors you can see. And this is like the sunset. Because of the clear sky, you have a very different and nice sunset there in Namibia. And here, these are some astrophotography I tried with my phone. These are not of a great quality, but at least with my phone, I could see the Milky Way. And also these 2 dots, if you can see, these are like LMC and SMC, like the galaxies in our local group. So this is pretty interesting. When you do observational astronomy, you get to go this kind of nice location where you can observe this clear sky. And all these observatories are located at very nice, beautiful places. So that's it. If you have any questions, please go ahead. And yeah, thank you.
Oh, thank you. Thank you. I think that was a very wonderful talk. So now the floor is open to questions. So
Yeah, sure. And I know, I mean, my board kiba kiba include korelo and probably tomorrow karne like too much information and ekwa hoy goise. So it's not like you have to understand everything. Tomorrow karne it will help koribo if you know the keywords. And basically, this is just to get familiar with like the TV emission, the detection techniques, and all other stuff. And later, if you find something interesting, you can follow up on it. And then, of course, you can always write to me or discuss with someone, some expert, because you know what to read or what to study. So yeah. Or apart from this, if you have any other questions like like a PhD or masters in abroad or anything related to research, you can ask.
yeah, I think that's a great piece of advice. So participants, kindly make the best use of the time. So please kindly interact with the speaker.
Yeah, you can ask anything like to like PhD. It's like if you want my honest opinion, like PhD, how difficult it is, or what are the pros and cons, and anything.
Yeah, I think it would be a good idea to give a brief overview about your PhD experience and probably how you got into those postdoc programs and all. Like this is a question that everybody who wants to go for
Sure.
higher studies have in their mind. So kindly go ahead with that.
Sure. Okay, so about that, okay, let me start with the basics. So tumalke jodi BC level at asa and tumalke jodi astronomy probably tumalko BC level to tumalko astronomy papers asa like basic astronomy, and tumalke BC level or tumalke you can try for some internships and try to do a small projects and get experience with like those optical telescope. And for example, tumalke moi Teachপুৰ University কথা ক'ব পাৰিম because Teachপুৰ University মই নিজে পঢ়া, so আমাৰ তাত এটা facility আছিল like optical telescope তাত তোমালকে গৈ observation তোমালকে visit কৰিব পাৰা আৰু তাত তোমালকে small internship কৰিব পাৰা as a BSc students. So তোমালকে এইবোৰ BSc level পৰা তোমালকে যদি ভাবিছা in future astronomy কৰিম, so তোমালকে like summer vacation or free time ত এইবোৰ কৰিব পাৰা. Then in masters মই astronomy specialization লৈছিলো Teachপুৰ University paper. And তাৰ পাছৰ পৰা like মাষ্টাৰ্ছত আমাৰ কি হয় এটা project থাকে, of course তোমালোকে জানা চাগে যে তোমালোকে এটা স্পেচিয়েলাইজেশ্যন লোৱা, তোমালোকে 1 year এটা project কৰিব লাগে. So আমাৰ এটা problem হয় কি projectৰ লগত আমাৰ papersও থাকে, so projectত ইমান focus কৰা নহয়, ইমান time নাথাকে project focus কৰিবলৈ, কিন্তু সেই master's projectটো বহুত important because it featured Bhaba research কৰিবলৈ a master's project to like the first-hand experience in doing something like towards the research. So that is very important. So we're going to try korba that master's project we're going to sincerely kora and hikini try koriba that kiba ta hika kiba ta idea lua and তোমাকে যদি observation যাব বিচাৰিছা যিমান পৰা data analysis techniques বোৰ শিকিবা, not just following some commands, তোমাকে বুজিব try কৰিবা how the detector works and তেতিয়া help হয় মানে visualize কৰাত বা বস্তুটো যিখিনি data পালা data খিনি interpret কৰাত বহুত help হয়. তাৰপাছত সেইখিনি তোমাকে মাষ্টাৰ্ছ লেভেলত কৰিব পাৰা। এণ্ড তাৰপাছত মোৰ PhD কাৰণে মই তেজপুৰ ইউনিভাৰ্চিটিতে কৰিছিলোঁ, কিন্তু ডক্টৰ ৰূপজ্যোতি গগৈ মেমৰ আণ্ডাৰত কৰিছিলোঁ। বাট তেজপুৰ ইউনিভাৰ্চিটি এটা ভাল আছিল কি সেইটো টাইমত আমাৰ আয়ুষৰ লগত কলাবৰেশ্যন আছিল, লাইক আমাৰ এইটো অপৰচুনিটি আছিল কি আমাৰ ইউনিভাৰ্চিটি ষ্টুডেণ্টবোৰে গৈ আয়ুষত গৈ তেওঁলোকে ভিজিট চামৱান এণ্ড দেন ৱৰ্ক উইথ চাম এক্সপাৰ্ট। So মোৰ সেইটো অপৰচুনিটি আছিল, মই প্ৰফেচৰ ৰঞ্জু মিশ্ৰৰ লগত কাম কৰিছিলোঁ আয়ুষত, এণ্ড তাতে মই বহুত এক্সপ'জাৰ পালোঁ, লাইক ডেটা এনালাইচিছ শিকিলোঁ এক্সপাৰ্টছৰ পৰা, এণ্ড তাৰ পৰা মোৰ লাইক ৰিচাৰ্চ ষ্টাৰ্ট হ'ল, লাইক ৱৰ্কিং অন প্লেজাৰ্ছ। তাৰ পৰা মোৰ কলাবৰেশ্যন BRCৰ লগত ডক্টৰ সুন্দৰ সাহানাথন। তেনেকৈ তোমালোকে যেতিয়া এটা কলাবৰেটিভ ৱৰ্ক ষ্টাৰ্ট কৰা, ইনষ্টিটিউটবোৰ ভিজিট কৰা, কলাবৰেটিভ ৱৰ্ক ষ্টাৰ্ট কৰা, ইউ লাৰ্ণ মোৰ এণ্ড মোৰ থিংছ ফ্ৰম দ্য এক্সপাৰ্টছ। তোমালোকে সেই PhD ডিউৰেশ্যনত যিমান পাৰা শিকিব ট্ৰাই কৰিবা দিছ টেকনিক্সবোৰ, অবজাৰভেশ্যনে হওক বা থিয়ৰিয়ে হওক বা চিমুলেশ্যনে হওক, যিমান পাৰা টেকনিক্সবোৰ শিকিব ট্ৰাই কৰিবা। লাগিলে ৰিচাৰ্চ পেপাৰ অফক'ৰ্চ এইটো মেণ্ডেটৰী, মিনিমাম এখন বা দুখনলৈ তোমালোকৰ পেপাৰ্ছ লাগিবই, বাট মোৰ দেন ডেট তোমালোকে যিমান পাৰা যদি স্কিলছ একুৱাৰ কৰা সেইখিনি তোমালোকক হেল্প কৰিব পাছত পষ্ট ডকত প্ৰবাবলি। চ' Yeah, and then postdoc karone tumalke of course agor speaker mention course keneke apply korbo lage, like there are different websites jot tumalkor so postdoc duta type thake, eta thake fellowship jetu tumalke এখন host institute লগত connect কৰিব লাগে, host লগত কথা পাতিব লাগে, and you then have to come up with a project, and then with that project তোমালোকে এটা project proposal submit কৰিব লাগে for different kind of fellowship. যেনেকৈ ইণ্ডিয়াটো বহুত fellowship আছে, abroadতো বহুত fellowship আছে, তোমালোকে apply কৰিব পাৰা. And fellowships of course সদায় বহুত prestigious হয়. It's a very good add-on for your CV in case of postdoc. But তোমালোকে apart from this fellowship, but these fellowships are sometimes very difficult, like Papa Karne, huge competition. But there are other postdoc opportunities like project postdocs, like a fixed term project, like for 2 years, 1 year. These are fixed term, and these are advertised in different medias like AA Job Register or other website. Tumalke paba, hebur mane every other month tumalke dekhi thakiba advertisement. Tumalke jodi bhaba kiba that interest, okay, 80 topic are interested, and you can apply, prepare a CV, prepare a nice research interest. That is very important, like tumalkor research interest keneke proposal to bunwa. So hikini, then there will be interview, and then yeah. So more project kita project postdoc hoy moi like advertisement like is job register follow kori aslu, then I saw more first postdoc karone moi PhD like extra kam kori aslu, but the postdoc karone I want to get involved into very high energy astronomy. So because these are close collaboration, if you're not a part of the that collaboration, you cannot learn much. So this is the reason I joined there, like in South Africa, because the telescope, the HASS telescope, is in Namibia, and there's a very like strong group in South Africa, like Northwest University, working on with the HASS data. So I wanted to be a part of that. So this is one of the reasons I joined that institute. And till now I'm continuing working with HASS. Also APCU, like Paris Institute joined Carlo, he institute 2 member of HASS collaboration. So that way I can continue. And these collaborations are really important because when you work in a collaborative team, you learn a lot from different experts. You have different opinions and bahut opportunities poa jay. And you know, that way you know people like field of manu chini poa, and tetia pasat postdoc apply korobole hubitha hoy. Yeah. So
Yeah, I think, yeah, that was quite comprehensive. And probably could you also share something about what are the master's opportunities? Because like many of our participants, they often ask this question, like, what if I want to do a master's in astronomy abroad?
Abroad, okay. মানে ইন্ডিয়াটো তোমালোকে জানাই, লাইক ইউনিভাৰ্চিটিজ আছে, ইনষ্টিটিউটছ আছে, ইনষ্টিটিউটত তোমালোকে কৰিব পৰা মাষ্টাৰ্ছ, ইণ্টিগ্ৰেটেড PhD থাকে, লাইক so abroadত কৰিবলৈ তোমালোকে এটা বস্তু লাগে ৰেকমেণ্ডেশ্যন, which is really important. আৰু মাষ্টাৰ্ছৰ কাৰণে তোমাৰ মই ইমান ক'ব ডিটেইল ক'ব নোৱাৰিম, বিকজ মই নিজে মাষ্টাৰ্ছ ইণ্ডিয়াতে কৰা, অসমতে কৰা, তেজপুৰ ইউনিভাৰ্চিটিত. But master's karane, of course, there are like procedures, application procedure follow koriba, and just keep applying. Just I don't know, telkor exam no hoy, just tumalke recommendation ta lage master's karane, and tumalkor jodi research kiba experience thake, it's better. And also for PhD, because the PhD korbo bisara. So master's karane is a standard procedure, tumalke just apply kora, just follow kora, keep procedure application. But for PhD, abroad koribo karone it's better tumalkor jeti olop masters or research experience thake, tumalke jeti masters project to bhalke kora, PhD karone it becomes easy to get a PhD in abroad. Yeah, but it depends on the institute. Tumalke kod masters apply koribo bisarisa bhalke, then you can just, the best way is like, okay, tumalke etu institute jabo bisarisa, ekta topic porhibo bisarisa, then you do a background check. Okay, etu institute, then you can find some students from that institute and interact, like what is the best way to, because different institutes or criteria are different. Like abroad is a very broad thing, right? Like different institutes have different criteria, and different country wise criteria would different hoy. Kismane tumar fellowship dibo, kismane fellowship karone kismane tuition fee nai, kismane bahut beshi tuition fee thake. So tumalke olop pekini already existing kunba jodi student ase telokor লগত discuss korle beshi benefit hobo. So tar karone tumalke university website page follow korbo para kun student ase, and you can connect them in LinkedIn or email them and ask the details.
I think that was quite a wonderful discussion that we had. So hope it will help
Sure.
all the participants. So probably it's also time to close up the meeting now. So I think we
Sure.
have, yeah. So let me just complete the formalities. So we have with us Dr. Novindu Dev. So he'll be delivering the vote of thanks for this meeting. So Dr. Novindu.
Okay. Hello. Can
Yeah,
you hear me?
yeah, Novindu, you are audible.
Okay. The talk was really very nice, Dr. Goswami. We had a wonderful session with you, and you had given such a nice insight to the overall things that you are doing, and about the methods, or I will say about the procedure to admissions into those higher education stuffs. Uh, Anyways, thank you for all the talks and all the elaborations that you did. And I also would like to thank the audience, the participants who eagerly participated in the program and who heard you, who have questioned you. Thank you very much for all the participants, and more such programs are coming up in future. Thank you, Goswami, once again.
Thank you very much. And
Thank you.
thank you very much for the opportunity. I had a great time.
Yeah, thank you. So probably when you visit Sam next time, please let us know. Maybe we can also.
Sure. My probably March or Goya. So
Sure.
yeah, coming. Yeah.
So Dr. Goswami, so probably we'll share your email ID with the participants so that if they want to contact you, maybe they can do it in the future, right?
Sure. Yes. Please go ahead.
All right. So thank you
Yeah.
for
I
your
mean,
time.
to the participants, I mean, to capacity question, I say you can write to me. You can connect me in LinkedIn or probably write to me to my like email. So yeah, you're most welcome to do that.
Yeah. Okay. So thank you once again for your time, and we were glad to have you. So any concluding remarks from your side?
No, that's fine. I had a great time. Like, thank you.
All right. Thank you for joining. See you. Bye.